we are going to talk about the Carnot cycle and the Carnot principles. Previously, we have introduced the concept of a heat engine and also the concept of a refrigerator. We are going to describe a specific cycle. It's called the Carnot cycle. That's used for either a heat engine or a refrigerator. This Carnot cycle is composed of 4 processes. And after going through these 4 processes, the heat engine or the refrigerator would return to its initial condition to complete a cycle. The 4 processes include 2 isothermal processes and 2 adiabatic processes. Here I show a figure, a schematic of a heat engine that's working in between 2 thermal reservoirs. Okay, assuming the working fluid is a ideal gas, then we can illustrate the 4 processes as on the PV diagram, showing how the processes would look like on the PV diagram by representing the conditions of the working fluid. Let's see. We have at point 1, point 1, let's say this is the initial condition. This is the initial condition where the working fluid would be. And in a isothermal process, if it's an isothermal heat addition process in which the heat engine would absorb heat from the high temperature reservoir, then the ideal gas working fluid would expand and its specific volume would increase, and its pressure would actually decrease if the temperature is kept constant. Okay, so we have this isothermal heat addition process in which heat engine takes heat from the high temperature reservoir to reach condition or state 2 of the working fluid. Then in the next process, the system, the heat engine, the working fluid expands adiabatically in such a way. And then we haven't really studied the adiabatic expansion process for ideal gases, but this is what a adiabatic expansion of ideal gas looks like on a PV diagram. Its slope is steeper than a isothermal process. Okay, and then when the expansion completes, we can see the ideal gas working fluid would have to reach a lower pressure condition and also with a larger specific volume. And we can tell in this process the heat engine must be doing work to the outside because the working fluid itself is expanding. So the system, if you consider the system as the ideal, as the working fluid in the heat engine, then this system would be doing work, would be doing moving boundary work. Let's consider a closed system. A closed system can be a heat engine. So this, in the process 2 to 3, we have a work output. So there's a work output. Then the working fluid would dump waste heat to the low temperature reservoir in another isothermal process. Okay, this is similar to the isothermal heat addition process, except it happens at a lower temperature from 3 to 4. In this process, there's heat transfer from the heat engine to the surroundings, or specifically to the cold reservoir. And then the ideal gas system, which is the working fluid of this heat engine, would have to go back to its initial condition to complete the cycle through a adiabatic process. In this adiabatic process, there will be work done from this environment to the working fluid. So there's work input. And then the heat engine would complete a cycle, and in this cycle there are 2 processes in which there is a heat transfer between the heat engine and the surroundings, one with the high temperature reservoir, the other with the low temperature reservoir. There are also two adiabatic processes in which there's work interaction between the heat engine and this environment. One outwards from the heat engine, the other inwards into the heat engine. Okay, what I did not mention is that the Carnot cycle is a ideal cycle, which means all the processes are reversible processes. So we can simply turn around and run all the processes in the opposite direction. Then we would have a refrigerator that runs on a Carnot cycle. So it's simply the opposite of the cycle that we described in the previous slide. You go this way. You have the initial condition, and you go down. You do the heating. The refrigerator would do some work to the environment, and then reach state 2, and then undergoes another isothermal process to take heat from the low temperature reservoir. And then there will be another process, adiabatic compression process, in which there will be outside work done to the working fluid to make it compress. And then there's a heat rejection process in which heat is dumped into a high temperature reservoir. So this is the cycle of a Carnot refrigerator. So the previous illustrations were two PV diagrams showing the cycles of either a Carnot heat engine or a Carnot refrigerator. Let me emphasize again, those two PV diagrams were only meant for ideal cycle, only meant for ideal gas as the working fluid of the heat engine or the refrigerator. So here we can visualize the Carnot cycle in a general sense. Alright, still, let's assume that the working fluid is still ideal gas. In the first process, we have the heat addition from this is a heat engine, this is a Carnot heat engine. So the first process is this process, and that's heat absorption from the high temperature reservoir in the isothermal process. Then you have a adiabatic expansion process, that's the process 2 to 3, in which case in this 2 to 3 process, the only interaction between the working fluid and the surroundings is work. There's no heat transfer because it's an adiabatic process. Then from 3 to 4, we have another isothermal process in which the heat engine would dump the waste heat into the low temperature reservoir. Then the final process is a compression process in which there's work done from the outside to the heat engine system. All right, I want to make another note here. We see a closed system that's used as a heat engine. It's also possible that we can use a steady flow process device as the heat engine. Let's see how that would work. Okay, this is an example of a series of reversible processes to realize the heat engine process, and then you can see or to realize the heat engine Carnot cycle concept. You can see in this case we have several components, 4 components in this dashed line rectangular box. We have a boiler, and in this boiler there's working fluid flowing through it. So continuously there's a stream of heat added into the boiler and to heat the working fluid in it. And if this is a isothermal process, and then this satisfies one of the processes for the Carnot heat engine cycle. The next process is a adiabatic expansion process in which there's work done by the working fluid to the outside. Now this can be realized through a turbine. Okay, so the working fluid goes into the turbine and then it expands in the turbine with no heat transfer, but because of the design of the turbine, there's work done, there's work output from the turbine to the environment, or to something that you need to produce work for. And then there's the third process. The third process is a condenser, in which the working fluid can transfer heat to the low temperature reservoir at a constant temperature. And the fourth process is a process in which the working fluid needs to be compressed and back to its initial condition. Here, let me say that the numbering is different than the numbering we used in the previous slides. So here, the heat addition process is 4:1. In the previous illustrations, the heat addition process is 1:2. So there's a shift in the numbers. All right, if we were to realize this heat engine process using water as the working fluid, this is how we may realize that. See, then this will happen all inside the saturation dome, so that we can utilize the isothermal heat addition and isothermal heat rejection process. The isothermal heat addition would happen when the water is in the form of a saturated liquid and saturated vapor. So you begin from a saturated liquid, and then you add heat to the working fluid. Its temperature will not increase, or you can do this. You can add heat to such a working fluid without increasing its temperature. What you change is the quality of the mixture. Eventually, you reach a limit. The limit is when you reach a saturated vapor condition, and you cannot add any more heat to it without increasing its temperature. So we stop here, and then we let the saturated vapor to expand in the steam turbine to do work to the outside. So there will be work out, and there's heat addition, and then after doing work in the steam turbine, the saturated vapor would become so-called a wet steam. It would become another mixture of a saturated liquid and saturated vapor, except at a lower temperature and lower pressure. So then this wet steam, this mixture of a saturated liquid and saturated vapor, would go through something called a condenser. It's basically a heat exchanger. In this heat exchanger, heat is taken out of the mixture of a saturated liquid and saturated vapor of water, so its quality further decreases. There's additional saturated vapor to become saturated vapor to become saturated liquid in this process. And then if you carefully choose your end point, you come to this point, point 3, and then you let that wet steam, your saturated liquid, saturated vapor mixture to go into a pump or a compressor. You can compress it back to its initial condition 4 in a adiabatic process. So this is how, in theory, we may realize a Carnot cycle using steady flow processes. Now, can you, in this case, identify the heat engine? Now, I would say the heat engine is everything that's included in this dashed line box. This whole thing, even though it consists of multiple components, this whole thing is the device that we can use to realize the heat engine function. Okay, and in particular, this one would work under a Carnot cycle with 2 isothermal heat transfer processes and the 2 adiabatic work interaction processes. Okay, next we're going to talk about the Carnot principles. Remember, the Carnot cycle is a reversible cycle. The Carnot principles are these. There are 2 statements. The first one is no heat engine can be more efficient than a reversible one that operates between the same two reservoirs. The second statement is that all reversible heat engines operating between the same two reservoirs have the same efficiency. Okay, we can prove the Carnot principles. Let's see how we prove the first one. This is the strategy. We do a thought experiment. We have two heat engines. One is what we call the any heat engine, and the other one is a reversible heat engine. And these two heat engines, the any heat engine and the reversible heat engine, work between the same two reservoirs. And each takes the same amount of heat from the hot reservoir. And then the second step is we make the any heat engine more efficient. Let's make an assumption. Let's make it more efficient. Then because the reversible heat engine has the advantage of it being reversible, we can reverse all its processes to make it into a refrigerator. And then the next is to show that this would lead to the violation of the second law. And then, because we made the assumption that the any heat engine is more efficient than the reversible heat engine, which led to the violation of the second law, then logically we should conclude that the assumption that any heat engine is more efficient than the reversible heat engine must be false. So the opposite should be true. Okay, this is the schematic that can help us show how this Carnot principle is proven. We have two reservoirs, two thermal energy reservoirs, the hot reservoir and the cold reservoir. And we have two heat engines. One is the any heat engine, and the other one is the reversible heat engine. They take the same amount of heat from the hot reservoir, and the assumption is that the any heat engine is more efficient than the reversible heat engine, which means this W produced by the any heat engine must be greater than the W reversible that's produced by the reversible heat engine. Okay. Then we still need to satisfy this first law of thermodynamics. You can see, because you take the same amount of heat from the hot reservoir, and if you produce more work, then you must dump less heat into the cold reservoir. So the Q sub L that's dumped by the any heat engine must be smaller than the Q sub L reversible that's dumped by the reversible heat engine. Alright, then comes the critical step. We reverse the reversible heat engine. We change the direction of the reversible heat engine. We make it into a refrigerator. Okay, and we actually we combine the any heat engine and the reversible heat engine into one thing. Now, in the previous slides, we have shown that you can have a device that's composed of multiple components and includes multiple processes, and then yet you can see that one combination of things as one device that's either a heat engine or a refrigerator. So this is what we do. We combine the any heat engine and the reversed reversible heat engine, which is a reversible refrigerator. Okay, let's see what absurd conclusion this will lead us to. This combination of the any heat engine and the reversible refrigerator as a whole is a device that does not take anything from the hot reservoir. Okay, it takes in heat here at QH, but it dumps that heat back into the hot reservoir in the same amount. So the net result is this combined device is not taking any heat from the hot reservoir. So it in essence it has no interaction. It doesn't have anything to do with the hot reservoir. And then let's see what the net result is. Okay, the net result is we have a combined device, a device that combines the any heat engine and the reversible refrigerator. What it does, it takes heat from the cold reservoir. Okay, it takes heat from the cold reservoir. There's a net amount of heat it actually takes from the cold reservoir, and what it does, it produces a net amount of work in this amount. Okay, we can see this is a device that interacts with only one reservoir and produces a net amount of work. This is a violation of the second law. Specifically, this is a violation of the second law as stated in the form of the Kelvin-Planck statement. Okay, after proving the first Carnot principle, the second one is quite easy. You can derive it from the first principle. You have to. This is how we do it. So, since we have proven that no heat engine can be more efficient than a reversible one that operates between the same two reservoirs, then let's have two reversible heat engines. Let's call them A and a B. Reversible heat engine and reversible heat engine B, they both work in between the same two reservoirs. Because we have proven the first Carnot principle, which says no heat engine can be more efficient than a reversible heat engine that operates in the same two reservoirs. So A cannot be more efficient than B. And on the other hand, B cannot be more efficient than A either. So they must have the same thermal efficiency. Okay, reversible heat engines do not exist in reality, but they're very useful. How are they useful? Reversible heat engines provide an ideal for thermal energy conversion. They tell us how what's the upper limit of thermal efficiency that you can get for any realistic heat engine. This is its main use. Okay, the Carnot heat engine, let's emphasize that again. The Carnot heat engine is a reversible heat engine that works between two reservoirs. That's how we can have the two isothermal processes and two adiabatic processes to complete the four-process cycle. And certainly it's possible that if you have multiple thermal energy reservoirs, you could have a reversible heat engine that operates in between more than two reservoirs, but we would not call that a Carnot heat engine. We can also have Carnot refrigerators and Carnot heat pumps. And we can show that such refrigerators or heat pumps, Carnot, that operate on a Carnot cycle would have the highest coefficient of performance when they work as refrigerators or heat pumps.